Example 7. Find the integral of tangent cube x dx. Solution. Here only tangent x occurs. So we use tangent squared x equals secant squared x minus 1 to rewrite a tangent squared x factor in terms of secant squared x. The integral of tangent cubed x dx equals the integral of tangent squared x dx equals the integral of tangent x open secant squared x minus 1 close dx equals the integral of tangent x secant squared x dx minus the integral of tangent x dx equals tangent squared x over 2 minus the natural log of the absolute value of secant x plus big C. In the first integral, we mentally substituted u equals tangent x so that du equals secant squared x dx. If an even power of tangent appears with an odd power of secant, it is helpful to express the integrand completely in terms of secant x. Powers of secant x may require integration by parts, as shown in the following example. Example 8. Find the integral of secant cube x dx. Solution. Here we integrate by parts with u equals secant x and du equals secant x tangent x dx and dv equals secant squared x dx and v equals tangent x. Then the integral of secant cubed x dx equals secant x and tangent x minus the integral of secant x tangent squared x dx equals secant x tangent x minus the integral of secant x open secant squared x minus 1 close dx equals secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. Using Formula 1 and solving for the required integral, we get the integral of secant cubed x dx equals 1/2 open secant x tangent x plus the natural log of the absolute value of secant x plus tangent x close plus big C. Integrals such as the one in the preceding example may seem very special, but they occur frequently in applications of integration, as we will see in Chapter 8. Integrals of the form the integral of cotangent to the power m x cosecant to the power n x dx can be found by similar methods because of the identity 1 plus cotangent squared x equals cosecant squared x. Finally, we can make use of another set of trigonometric identities. These product identities are, this is the sidebar, these product identities are discussed in Appendix Big D. Back to the text. Finally, we can make use of another set of trigonometric identities. Equation 2, to evaluate the integrals, part A, the integral sine of mx cosine nx dx Part B, the integral of sine mx sine nx dx. Or Part C, the integral of cosine mx cosine nx dx. Use the corresponding identity. Part A, sine big A cosine big B equals 1/2 open bracket sine open big A minus big B close plus sine open big A plus big B close bracket. Part B, sine big A sine big B equals 1/2 open bracket cosine open big A minus big B close minus cosine open big A plus big B close bracket. Part C, cosine big A and cosine big B equals 1/2 open bracket cosine open big A minus big B close plus cosine open big A plus big B close bracket. Example 9, evaluate the integral of sine 4x cosine 5x dx. Solution. This integral could be evaluated using integration by parts, but it's easier to use the identity in equation 2a as follows. The integral of sine 4x cosine 5x dx equals the integral of 1/2 open bracket sine of negative x plus sine of 9x close bracket dx equals 1/2 the integral open negative sine x plus sine 9x close dx equals 1/2 open cosine x minus 1/9 cosine 9x close plus big C.